Alright, so what we're going to do today is we are going to talk about precipitation reactions. Okay, now a precipitation reaction is a reaction that occurs when we take two solutions. Here I've labelled them solution 1 and solution 2. Each contain two different ionic compounds, here A and B, and we mix them together. So we pick up solution 1, pour it into, and we now have a combination, a mixture of the two solutions. Alright, and so when we do this, depending on what the compounds A and B are made out of, there is a possibility that a precipitation reaction will occur. Okay. Now, this possibility, whether or not this happens, is dependent on what the compounds A and B are. Okay, so if we look over here, we have a table, and in the left-hand column, we have four different ions, and these ions are what we call always soluble. So no matter what ions these four are exposed to, if any of these four are exposed to any other ion, they will never form a precipitate. They are always soluble. On the right hand side, we have three ions which are usually insoluble. So what that means is that they are the opposite of these four. These guys over here are always soluble. These guys always form a precipitate, no matter what they're mixed with, except if the two are mixed together. If the two are mixed together, then this side wins, and we have no precipitate. Okay, and so if we want to precipitate the form, up here we've got lots of little red dots in here. These are the ions. In real life, these ions, we won't see these red dots at all. Okay, but I've drawn them in here just to show that there are two compounds in here, each containing both positive and negative ions. Okay, and compound A contains positive and negative ions. Compound B contains positive and negative ions. Okay, so depending on what these positive and negative ions are, a precipitate may form in this resultant solution. So, if we mix the two together and we get a bit of solid forming inside, a bit of visible precipitate. So up here the red dots, they're invisible. They're ions which are dissolved. We can't see them. Here, when a precipitation reaction occurs, the ions in each of these solutions combine and form a solid. And so here is a beaker in which a precipitation reaction has occurred. Okay? And so assuming compounds A and B, so solutions 1 and 2 have mixed and created a precipitate inside this solution, which is a mixture of the two, we can figure out a possible combination of these. Okay, so if we have on the right hand side, if we have compound B, okay, and now we look at the possibilities. So because a precipitate formed, we'll assume that one of these three ions was in solution 2, was the anion that formed a part of solution 2. So we'll choose hydroxide. So we'll say hydroxide in solution B. Okay, and we'll say because solution 2 was in fact a solution, because compound B did dissolve in water to form the solution, we know that the hydroxide ion must have been with one of these three. So we'll say it was with potassium. So now we're looking at the compound. So we no longer need the charge there. Alright, and so we've got that as compound B. And now for compound A, so we're assuming that a precipitate is formed here. So compound A must therefore have a cation which is not one of these three. Okay, so we've formed a precipitate over here, and we know that because potassium is always solid, no matter what the anion, the negative ion that could possibly pair up with potassium, we know that whatever that is, the potassium will not form a precipitate. However, we know that hydroxide is in fact usually insoluble, and so depending on what the cation in compound A is, a precipitate will have formed here. So we're going to assume that a precipitate did in fact form, and therefore that the positive ion in solution 1 was not one of these three. Okay, so what we'll have a guess, and we'll say that magnesium was the positive ion here. So if we say that, so as a result, let's assume that here we have magnesium hydroxide. That is the solid that's formed, okay? So we write OH2. That 2 should be outside the brackets there. And so that's because magnesium has a 2+ charge, magnesium ion does. And hydroxide has a singular minus charge. And so we need 2 hydroxide ions for every magnesium ion. Okay, so we'll assume that that's the precipitate that's formed, magnesium hydroxide. Okay, and so therefore we'll call compound A magnesium nitrate. Because you know that nitrate is always soluble, and therefore magnesium nitrate will in fact be able to form a solution over here. So we'll call that Mg and NO3 brackets 2. Okay, and that's just simple. Nitrate ion has a single negative charge. We know the magnesium ion has 2 positive charges. So we need 2 nitrates for every magnesium in order for A to be a stable and neutrally charged or no uncharged compound. Okay, so what we see if we've added compounds A and B together, potassium hydroxide, soluble compound because potassium is always soluble, and magnesium nitrate because this is soluble because nitrate is always soluble. If we add them together, because we know that hydroxide is usually insoluble with everything except this column of ions over here, we know that magnesium hydroxide will in fact form a precipitate. Okay, and so in that case we know that solution 2 will form a precipitate. So we can write a full formula equation for this. So we can write potassium hydroxide, and now these are in solution, so we write this as aqueous, added to magnesium nitrate will produce potassium nitrate. So to balance this out, we're going to see that we need a 2 here, as we've got 2 hydroxides for every magnesium. And so therefore we have 2 nitrate. Okay, and what's important here is that potassium and nitrate, they're both always soluble, so this will definitely be aqueous. Meanwhile, we know that the magnesium hydroxide forms a solid. Okay, so that is the full formula equation. Now if we want to write this out differently, we can write it out as an ionic equation. So what we have in here are 2 ions. We have Mg, we have magnesium ions, and we have nitrate ions. Okay, because we don't actually have magnesium nitrate in sort of a combined consistent form where magnesium and nitrate ions are all connected and bonded together. They're all separated, they're all dissociated in this solution. And the same goes with potassium hydroxide. Because it's in solution, we know that the potassium and hydroxide ions aren't actually bonded together, they're just floating around by themselves. So what we have is four different species inside these 2 solutions. So when we mix them together, we have 4 different ions all mixed together in one solution. Okay? But what happens is that we know that after we mix them together, we come out with a potassium nitrate in aqueous form still, which is very important, and magnesium hydroxide in solid form. Because this is an aqueous form, again, the potassium ions and the nitrate ions are dissociated. So they're still just floating around by themselves. The potassium and the nitrate are not yet bonded together. They're still floating around by themselves. So if we were to write a chemical equation, an ionic equation, with everything written as ions rather than as compounds, we would have a nitrate ion here, and a nitrate ion on the left-hand side, and a potassium ion. We know that there's other stuff around, except we know that these two things are unchanged. Because here, they're both just in their ionic form. They're dissociated, they're floating around by themselves. And when they combine, they're not actually forming a solid or a precipitate, so nothing's happening. So if we were to write an equation that included those, it would be pointless writing them on both sides because they're not undergoing a change. Here, we have these two ions in their aqueous form. I haven't written aqueous, but we know that they're aqueous in all forms, so it's the same thing there, and here. Okay, but we know that nothing happens here, so there's no point writing that out as part of the equation. So what we do is we can get rid of that when we're writing an ionic equation. We can get rid of those, and those are what we call spectator ions. Spectator ions are basically those ions that, in this reaction here, don't actually undergo anything. They don't undergo a change. The potassium ions and the nitrate ions are initially floating around up here by themselves, not touching anything, and later on they mix in two solutions now in one beaker, and they're still in aqueous form, so they're still floating around. Nothing's changed. On the other hand, however, the magnesium and the hydroxide ions, while previously they were floating around in these two solutions, when they've come together, they've formed a solid. So here it is appropriate to write an ionic equation including magnesium and hydroxide. Okay, because when we have an ionic compound in solid form, we can't write it as individual ions. We have to write it like this. We have to write it with the full chemical formula of the compound intact. Whereas in solution, we're allowed to split them up and write this potassium hydroxide as potassium ions and hydroxide ions. That's only possible because in solution they're both separate and they're both floating around by themselves. So if we want to write an ionic equation for what we have initially, we have magnesium ions floating around in solution, like that. Obviously they are aqueous, and this time it is important because there will be a change in the state of the ions involved. Okay, and we're combining it with hydroxide ions. Which are, again, aqueous to begin with. Okay, and so now, unlike last time when no change occurred and so the ionic equation was effectively useless, here these ions are in fact combining to form a solid. Okay, so there is actually a change, and because they're a solid, they're no longer separate and by themselves. These ions are bonded together. And so what we write is, now we need two hydroxide ions again because of their charges, which means that we're going to need a 2 on the other side. Okay, and now this is solid. Okay, so what we see here, we can write this reaction two ways. We can write it as potassium hydroxide in solution 2, in aqueous form, being mixed with magnesium nitrate in solution 1 in aqueous form, although I haven't actually written that here, in aqueous form. Okay, and they are producing potassium nitrate in aqueous form again, as well as magnesium hydroxide, however in solid form. And so because when ionic compounds are in an aqueous state, they're effectively broken down into their constituents. There's no point writing out potassium ions and nitrate ions in this ionic equation. Okay, there's no point because there's no change. They are spectator ions. They're not involved in the reaction. However, although the magnesium hydroxide ions begin in a similar state, they are combined through this reaction, through this precipitation reaction, into a solid. And so therefore, the ionic equation for the reaction includes only magnesium and hydroxide. We'll do an example on precipitation reactions in the next video.